Hello everyone and welcome to A+ Physics. Today we're going to take a look at the 2018 AP Physics 1 free response exam. A link to the test itself is in the notes below. So what we're going to do is just take a quick walkthrough of the free response questions on the test. Now, just a heads up, as we do this, I have not seen the official solutions or scoring guide yet. So this was my attempt at taking a quick look at the problems, maybe give you an idea of how to go after them. Chances are I made a couple silly mistakes as we go through here, but hopefully it at least gets you an idea of how I might go about attacking these problems. So let's dive in and look at number 1. Talking about a spacecraft with some mass moving in a clockwise circular orbit around the Earth. All right, it says in the figure below, draw and label the forces that act on the spacecraft. Let's see here. So I would probably, looks like our spacecraft is somewhere over here in this position. What I would do as far as the forces there, it looks to me like there's only one force as it moves in a circular orbit, and that will be toward the center, and that would be the force of gravity, Fg. And I think that would cover you for 1A. Now for B, it says we're going to derive an equation for the orbital period t in terms of mass of the spacecraft, mass of Earth, the radius, and any physical constants. This, to me, looks like we are looking at deriving Kepler's third law, which chances are you've probably done this in class at some point. Oops, I think I jumped ahead a little bit. So let's give that a shot here. First thing I'd look at is the net force that we have going on here. And let's see, we've got the net force is a centripetal force, so that's going to be mv squared over r, which is the force of gravity, so that's big G. We have mass of Earth times the mass of the spacecraft divided by r squared. Now, looking at just the right-hand side, or looking at this part of our three-part equation, we can solve that in terms of velocity to find out that v squared equals gme over capital R. The mass of the spacecraft cancels out. And then recognizing v equals d over t, we've got a constant velocity, or t, our period, is equal to distance divided by velocity, where our distance is going to be once around a circle, the circumference, 2 pi r. We could write this as d squared over t squared equals gme over r, or d squared, that's going to be 2 pi r squared over t squared equals gme over our radius. Just a little bit of algebraic rearrangement. T squared times g times the mass of the Earth equals r. Let's see, what do we have here? R times, oops, that'll be our capital R for our radius, 4 pi squared r squared. Solving for the period gets me square root of 4 pi squared r cubed over g me. I think that covers you for the period. All right, so there's our 1B part 1. For 1B part 2, it's now asking us what happens if we place a second spacecraft of mass 2m in circular orbit with the same radius. What happens to the period? Well, as I look at the period here, there's no dependence on the mass of the spacecraft, so for that part, I would say that it will be equal. Why not? Explain that the period has no dependence on the mass of the spacecraft. And then that moves us over here to part C. And on part C, it says this first spacecraft is moved into a new circular orbit that has a radius greater than r. What happens to the speed of the spacecraft compared to the original speed? Well, for part C, I'm going to go with less than. And the reasoning there is the speed, the square of the speed, is equal to gme over r if we come up here and look at our previous derivation. If we take that right from there, v squared is gme over r. So as r increases, that means our speed must go down. So I probably explained that in a sentence instead of just the symbols, but should give you a pretty good idea of one way you could go about answering that question. And with that, especially since it's a time test, let's quickly move along to question 2. Now in this question, we've got our conductive dough, basically Play-Doh, except I don't think they want to give brand names here. And what we're going to do is mold it into cylinders with different cross-sectional areas A and lengths L. It's a lab I oftentimes do in my classroom. If you want to do it at home, absolutely you can do it, but make dough that uses salt, not sugar, because the salt will help make it conductive. The sugary dough isn't very conductive and doesn't work as well. You can also just go buy Play-Doh from the store. The student apply a potential difference across the ends of it to determine the resistance, and those are our results right there. Then the students want to determine the resistivity of the cylinders. What could you graph in order to do this? Well, I would note that the resistance of a cylindrical resistor is rho L, the resistivity, times the length divided by the cross-sectional area. So if we're looking for rho resistivity, that's going to be RA over L. So what I would probably graph, if I wanted to do this in a nice way and have this come out as a slope, I'll put RA on my y-axis and length on my x-axis. So I'm going to need to graph another quantity, resistance times cross-sectional area, which would be in ohm meters squared. And I'll quickly just fill in the chart of what I got here. 0.015435, and as we were pressed for time, I didn't worry a whole lot about sig figs, just copied down what came out of the calculator quick. More time, we could be a lot more accurate, but again, you've got 5 questions to get through in just a short period of time. So what would we put on the vertical axis? On the vertical axis, I would be putting RA, and on the horizontal axis, I would put L. So RA on the y-axis, L on the x-axis. Now for part 2, it actually gives us a grid to go plotting this. Pick your scales, put your labels in units. So we would have down here L in meters, on the y-axis R times A in ohm meters squared. Would kind of be nice if they gave us just a little bit bigger graph here. So let's see, something like 0.03 meters, 0.06, 0.09, 0.12, 0.15, 0.18, 0 and up the left-hand side, 0.01, 0.02, 0.03, 0.04, 0.05, and I cheated and I added a 0.06 just so I could use more of the graph here. And then you just go through and plot your points. And without drawing the particular points in there, basically you get something sort of linear. I think my last point was way up here somewhere. Draw your best fit line. Mine looked kind of like that. Again, not taking a whole lot of time to plot points here, but you get the idea. And then it says use that graph to estimate a value for the resistivity of the dough cylinders. Well, we already figured out how to do that. Our resistivity is going to be the slope, which is rise over run, which is y2 minus y1 over x2 minus x1. Now, when you do this, don't use data points. Go pick a couple convenient points on your graph. And I always recommend to help the readers do this, try and pick points toward the end of the lines, toward the extremes of the lines, so you get the most resolution possible. And circle those points that you happen to use. So I don't know what would be convenient points. Maybe something like that. Circle those 2 points, fill in their values with units for y2 minus y1 and x2 minus x1. And when I did that, I got something on the order of about 0.4 ohm meters. So that's how I would find the resistivity of the dough cylinders nice and quickly. Now, it says for part B, another group of students performed the experiment but shaped the dough into long rectangular shapes instead of cylinders. Will this change affect the value of the resistivity determined by the second group of students? And that's actually a pretty complicated question, especially as you get further into electrical fields and field theory and how that's actually going to play out in those shapes of dough. At the level we're going through in AP1, though, really it doesn't make any difference. Resistivity does not depend on the shape. It's the cross-sectional area. Resistivity equals rho L over A. So I would say no. R equals rho L over A is a reasonable model for rectangular resistors as well as cylindrical resistors, and rho resistivity is a material property of the Play-Doh, not dependent on the shape of the Play-Doh. So at the level of modeling we're doing, we're using the R equals rho L over A model, I think we are all set. Now, in actuality, you might get some different results because we're using just a single wire to put current in and out at a point at each end of the resistor, but that's beyond the scope of AP1. So I think that covers us pretty well. No, resistivity does not depend on the shape. It's a material property of the Play-Doh. So that covers us for B. And then C, describe an experimental procedure to determine whether or not the resistivity of the dough cylinders depends on the temperature of the dough. Well, if you recall from our content, we do know that the answer to that is going to be yes. Typically, resistivity increases as temperature increases. It's not till AP2 that you really get into the why of that. But what sort of experiment could you do? And there are tons of things you could do. But to answer just that question simply, and I'm not sure I would actually do this in the lab, but with the equipment that's easily available in the lab I have in my classroom, what I would probably do is form the dough into a cylinder and attach a multimeter, put it in resistance mode to each end. We have meters that will measure resistance, multimeters that will do that specifically. So I'd place the thermometer in the Play-Doh and place it in a hot plate with the multimeter attached to each end, with it in a cylindrical shape. So cylindrical shaped dough, attach a multimeter to it. There's our multimeter. It's going to read out something in ohms. And then I'm going to stick the whole thing on a hot plate. There's our hot plate. Heat it up, measuring the temperature as it heats up, and every 30 seconds record the temperature from the thermometer and the resistance from the multimeter. We're not changing the shape or any other variables, so if resistance isn't changing, then resistivity isn't changing. If resistance is changing, resistivity is changing. So not a very detailed experiment, but to my mind, that would be enough to very simply answer question C. And again, if we were doing a whole lab on this, we'd probably put a lot more into it, but we're trying to answer this quickly and giving just enough detail so another student could replicate it and answer just the question given. So I would probably go that way. And you could certainly make an argument that on a hot plate, we're going to dry the dough out. That could change its resistivity a bit and different things. You could also look at putting it in a plastic bag, dunking it in water of different temperatures to let it come to an equilibrium temperature, measuring it at different temperature points. And on to question number 3. In this question, we have a disk that spins about the axle at its center, and an experiment shows us that the friction between the axle and the disk exerts a constant torque. That's nice. Constant torque is going to mean a constant angular acceleration. So at time t equals 0, the disk has an initial counterclockwise positive angular velocity omega naught and comes to rest at time t1. Fill in the graph on the left. Well, we know it initially starts at omega naught. It ends up down here at 0, and with a constant angular acceleration because of the constant torque, we must have a constant slope, where the slope of that is going to give us our angular acceleration. So there's our left graph. And for the angular acceleration, again, we have a constant negative slope. We must have a constant negative angular acceleration, where the value of this would be equal to the slope of that. So that covers us for part A. Now for B here, we find out that the magnitude of the frictional torque is tau 0. Find an equation for the rotational inertia. So we can go to Newton's second law for rotation to derive this. Net torque equals I alpha. Now, as we do this, being in a bit of a hurry on the exam, I wouldn't focus so much on signs, instead focus on the magnitudes here. So if you end up with the negative number going too fast, I would only come back and fix that at the very end of the exam if you have the time. But for now, I'd focus on the magnitudes here. We know the angular acceleration is omega final minus omega initial over our time, which for our problem, omega final is 0, omega initial was omega 0, divided by time t1, so that's minus omega naught over t1. Now, looking at our net torque, it looks like we have negative tau 0 equals I alpha when we cover our directions. But again, if you're not catching that, don't worry about it. Just focus on magnitude quickly, come back and get that extra point or two, assuming that they're even looking for that point later on. This should be a nice quick problem for us. Therefore, moment of inertia is minus tau 0 over alpha, or minus tau 0 alpha is minus omega naught over t1, which works out to be tau 0 t1 over omega 0. And again, if you had a negative sign, just focus on the magnitude, right? Something like magnitude, I equals magnitude of that answer. Come back and worry about signs later if you need to. So that covers, part C. Now we're going to graph this, knowing the disk in another experiment, the disk has an initial positive angular velocity, omega naught, at time t0. So it looks like we could fill in this point again on our graph. At time t equals 1/2 t1, the student starts dripping oil on the contact surface to reduce the friction. So it looks like we'll have the same graph up until we get to 1/2 t1. I can fill that in here. But now, as we add friction into less friction into the mix, we're going to have less angular acceleration. Therefore, our graph, and it's going to be changing, our graph is going to get a little bit of a curve to it. So I would probably do something kind of like that. And that's supposed to be concave at a fairly linear, not linear, at a fairly constant rate. So I'm not sure I drew that so well. Let me try that again. Something like that. You start to see the curve in there. All right, and then the grid at right, sketch the disk's angular acceleration, function of time from t equals 0 to t equals t1. Well, we'll start up to t1 with the same thing, and then we're going to have a changing angular acceleration that's going to get closer to 0. I drew mine as linear, but I'm not sure it makes it clear that that would be the case. It could be curved as well, as long as it is coming closer to that 0 point. But that, to me, would be the simplest way to do that one. So I think that covers us pretty well for part C. And now for part D. We're trying to mathematically model the magnitude tau of the torque from t times t greater than 1/2 t1. So while we're having that oil drop on there, which of these two equations would be the better mathematical model? Well, before I even look at those, the first thing I would note is I think torque should decrease over time. So we should see less torque as time increases. The only graph that's, the only model, the only equation that supports that is number 2. 2, we have t in the denominator. So as t increases, we're going to get less torque. So I would say that 2 is better and plausible, since torque decreases as time increases, which is what we would expect. Beyond that, I don't think we have to go any further to analyze that model to see just how accurate it is. We've answered the question as they have proposed it. Limited time. I'm going to move on to question 4. In question 4, here we go, our wave question. We've got a transverse traveling wave heading to the right along a string. We've got a couple dots on the string. Those dots are labeled P and Q. That's nice. The figure shows the string at an instant in time. Dot P has maximum displacement. Q has 0. Draw an arrow indicating the direction of the instantaneous velocity of the dot. Well, right away, at this bottom point here, at point P, I would say right there we have a V equals 0 point at that instant. And draw an arrow indicating the instantaneous velocity of the dot at point Q. Well, to my mind, that's going to be going up in the next instant. These points on a transverse wave can't go left or right. They have to go perpendicular to the wave, so up or down. P is just at that inflection point where it's shifting directions. Instantaneously, its velocity is 0. Q is moving up as the wave travels to the right, and that point Q rides along the wave, so to speak. All right, for part A2, the figure below shows the string at the same instant as shown in part A1. At each of the dots P and Q show the instantaneous acceleration of the dot. All right, well, the acceleration of the dot down here would be upwards. It is going to be, oops, don't know how I happen to do that. It is going to be accelerating up. That's the direction of the acceleration at that point. Q, on the other hand, at this point, is at the acceleration equals 0 stage. It is at the constant velocity point right there. So that should cover us for part A, I believe. Now we go and we take a look at part B. Part B says on the grid below, draw the string at a later time, t equals period over 4, where t is the period, capital T is the period of the wave. All right, and it gives us a practice grid. Hopefully I won't make any mistakes, but thankfully I have an eraser, so kind of cheating. But it looks like the period of our wave is quarter wavelength period shifted to the right. I'm going to start down here at -8, 0 up here at 12. We'll be up there, and plotting these points helps me draw the waves a whole lot more easily. So I think we're probably looking at something kind of like this. And from there, I'll try and fill in the wave with my best art skills. So I think we're looking at something like that. All right, and now if we look here, let's throw in our point P is right here at about the 18. There's P. And yeah, I think that covers us pretty well there. All right, on your drawing, draw a dot to indicate the position of P. Clearly label with the letter P. All right, did that. And for part C, consider the wave at time t equals capital T at the time that it's at 1 full period. Determine the distance traveled, not the displacement by dot P, between times t equals 0 and t equals the period capital T. Well, it looks like P in our drawing started down here at -8. So let's see, here's our wave. We had P starting down here. It travels 8 centimeters up, then 8 centimeters up, then it's going to travel 8 centimeters down and 8 centimeters down. 8, 16, 24, 32. I'd say its total displacement will be 32, pardon me, not meters, centimeters. Units are important. Centimeters as its total displacement in 1 full period of the wave. So I think that covers us for question 4. Leading us to our final question of the exam, number 5, our spring block oscillator. All right, we've got a spring attached to a mass m, moving with period capital T sub p and amplitude a sub p, about the equilibrium position x0. That's tough to say. We're going to drop a second block, twice as massive, on top of it. The instant it passes through the equilibrium position, it sticks to the top of block P and then oscillates with the new period TPQ and amplitude APQ. Find the numerical value of TPQ over TP. Well, let's figure out the period first for TP. 2 pi square root m over k is our formula for period of that spring block oscillator. And for TPQ, it's 2 pi square root. Now we have 3m over k. Spring constant stays the same. We've got the same spring. So there's our model. So all we need is the ratio of TPQ over TP, which will be 2 pi square root 3m over k divided by 2 pi square root m over k. Little bit of algebra should work out to be square root of 3 as the ratio between those two. All right, that wasn't too painful. Now for part B, let's see, how does the amplitude of oscillation of PQ, the two-block system, compare with the original amplitude? And I would say that APQ has to be less than AP. And in a clear, coherent paragraph-length response that may also contain diagrams and equations, explain your reasoning. All right, I'm not going to make you guys sit here and watch as I go through a paragraph, but I'll highlight some of the points you might want in there. First off, I would say the conservation of energy at the maximum compression, all energy is stored in the spring. So potential energy in the spring is 1/2 kx squared. We also have conservation of momentum to bring into this. The addition of the 2m mass triples the mass, so that's going to cut momentum, mv, that cuts the momentum in 1/3. The velocity gets cut in 1/3 because of momentum. Mass is increasing. We've got conservation of momentum, so we're going to have velocity is 1/3 that initial velocity, or the velocity with just p there. So let's call that VPQ. Now, our initial kinetic energy was 1/2 m, and we have v squared. That's our initial velocity. Now, our new kinetic energy, max, is going to be 1/2 times 3m, but our velocity is 1/3 the initial. So that's going to be v over 3 squared, which is going to be 1/2 mv squared over 3. So we have less kinetic energy in this new configuration. If we have less kinetic energy in this new configuration at its maximum kinetic energy, that's going to lead to less spring potential energy when that kinetic energy is 0, when you're at maximum amplitude. Therefore, less amplitude at PQ. And there are a number of ways to put that and calculate it. I think you can walk through them in a number of different situations, and I've even seen a couple folks looking at different ways to solve that. But I would put something like that into a paragraph-length response. This is one that I would probably think through a little bit, plan out my strategy, and then write the sentence once you've got it in nice mathematical terms. But overall, tests seem pretty reasonable, I thought. 5 questions covering the scope of AP1 pretty well, and nothing in there that seemed overly unreasonable or strange. So overall, I think a pretty solid free response test for 2018 AP1. Again, I probably did 1 or 2 things silly there, but I tried to take this test nice and quick like you guys have to as you take the exam. So hopefully it at least gives you an idea of how to go about attacking these different problems. And you can definitely look up the scoring guides when they come out on the College Board website. Those are usually available within a couple months. Tells you how you score each question point by point. Thanks so much for your time, everybody, and make it a fantastic day.